All right, so recall we were doing scintillating stuff on Friday with reducing matrices to reduced echelon form or reading of solutions of equations. So I did give you the vocabulary where we said the equation or the system of equations ax equals b is consistent if it has a solution but we saw that it could happen that you would have no solutions. It's inconsistent if it has no solutions. So for example, come on guys. So for example, you could have one equation that whose solution set looked like this, another equation whose solution set looked like this, and you'd be all happy and say, okay, I see what my solutions are, right? You have a line of solutions here. But then along comes a third equation whose solution set is disjoint from this line, and there aren't any solutions, right? There's no points that are in the yellow plane, the blue plane, and the brown plane. So that would be inconsistent. And that shows up how from our echelon form stuff. So this phenomenon, inconsistency, is recognized when the echelon form, you don't even have to be reduced, has something like a row of zeros, but then something non-zero on the right-hand side. Because that equation would say 0x1 plus 0x2 plus dot 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 plus 0xn equals 3. And there's no real numbers x1 through xn that make that work.
They're imaginary.
No.
Surreal.
So I want to talk today about some important words. So here's a definition. The rank of an m by n matrix A is the number of non-zero rows in any echelon form of A. Does somebody have a quibble to quibble? Cal looks like he wants to quibble.
I guess I was just going to ask, do you mean like 0 all the way through, or just like zeros on the left, like no solution type rows?
So I'm not talking about augmented matrices, although if you want to think of the augmented matrix, I mean the whole row anyway.
Okay.
So when I say non-zero rows, I mean rows that have some non-zero entry in them. So a zero row is all zeros everywhere. Still, is there a quibble? You philosophers should be catching me.
Just talk to Socrates real quick.
Yeah, right.
See what he has to say.
Is there not some theorem lurking in my definition?
You can have the same number of non-zero rows in any echelon form.
Yeah. I seem to be stipulating here that any echelon form of A and any other one have the same number of non-zero rows, even though we agreed they could have different echelon forms. So there's actually a theorem lurking in this definition. We'll have other situations where that happens later this semester. So the remark here is, we'll see soon why any two echelon forms have the same number of non-zero rows. So okay. So now what you might observe, so the rank is an important number. We'll usually call R the rank. So you have echelon form of A, looks something like this, right? Junk, and then zeros here, and then you might have all zeros here, and then another pivot, and then you might have, so you have to have zeros here, and then you might have another pivot here, and then you might have all zeros everywhere. So what would the rank be in this case? 3. How many pivots do you have? 3. So note you have, there's a pivot in each non-zero row. So if you were thinking about this as an augmented matrix, which is what Cal was thinking about a minute ago, and you were thinking of solving equations, so you would have started with your augmented matrix A with B on the side, and you would have row reduced and got it down to some echelon matrix. Let's say you go all the way to reduced echelon form. So this is not reduced, but if you went all the way to reduced, then you know how to read off the general solution to the system of equations from this. That's what I showed you how to do last time, right? What did we do? We solved for the pivot variables once we were in reduced form. We made sure that there were zeros below all the pivots. That's what echelon form has. But then reduced echelon form, remember, you cleared out above as well. So you used reduced echelon form to solve for the general solution. And how did we do that? In words, how did we do that?
So should make each row different coefficients. So that first one would be x1 and this one.
So you solved for,
You solved for
The
the ones,
vector
yeah.
X,
you solved for the pivot variables in terms of the free variables. So free variables were all the ones that weren't pivots. So you'd have free variable here, free variables here. So what do you notice in general about the general solution? You take the pivot variables and you write them in terms of a constant from over here. All right, so there's some constant. And then you have an expression involving the free variables. Oops, involving. And you do that for each of the pivot variables.
So what is the use of echelon form when you just go a step farther and create a reduced row echelon or reduced echelon form and just make it so much easier?
Because if you use echelon form rather than reduced echelon form, you're going to have your other pivot variables mucking up your expression for preceding pivot variables.
I'm saying, what is the use of using echelon form?
I misunderstood your question. Because if you're not trying to write the general solution, it can still tell you lots of things about rank and consistency.
Okay.
So you don't need to go all to this extent, as you will see. So what do we see? We see that our general solution looks like x as some vector of constants plus a linear combination of things that look like vectors times free variables. So I'm being a little sloppy here. This would be first free variable. This would be your second free variable. This would be your third free variable, and so on. So for each free variable, you get a degree of freedom in this solution. So I want to now address questions about how many solutions you have. So what would it mean to say that a consistent equation, a consistent system, so consistent means it has a solution. We didn't get a row of zeros here with a non-zero thing there. It has to have zeros there. A consistent system has a unique solution when what is true? There are no free variables, right? Free variables are giving you, as the free variable varies, you're getting infinitely many solutions to the original equation. So if you have a unique solution, there are no free variables. So how can there be no free variables? Think about this diagram here. How can you have no free variables? Careful, you're on the right track. Every column has a pivot. Every column has a pivot. What does that mean then?
That n is equal to the rank.
The rank. How many pivots do we have to have?
M.
So at this point you need to enunciate extremely clearly.
M.
M or N?
N.
M as in matrix.
M and matrix.
M as in mastodon or N as in nerds?
I think N. N as in nerds. N because column is
All right, I hear a few nerds. Is there anybody rooting for mastodons?
What is a nerd?
I thought Dan said M.
I'm gonna change my answer because Matthias said.
So the rank has to equal, there have to be, exactly as Tori said, there has to be a pivot in every column so that there are no free variable left over. So you have to have as many pivots as there are columns, and that would be N.
Yeah. Okay.
Mm-hmm.
Doesn't like the idea of consistency, doesn't that mean that whenever you have ax equals the zero vector, that's always consistent, right?
Mm-hmm. That's always consistent, because 0 is always a solution. Yeah, so let me comment. I think I said this the other day, but let's say it again. Comment the homogeneous system ax equals 0 is always consistent because the zero vector is a solution. Cal.
If every column has to have a pivot for it to be a consistent system with unique solution, but there are more columns than rows, can a row have more than one pivot?
So if there are more, good point,
So long as you have.
observation, thanks to Cal. If n is bigger than m,
There's no non-unique solution.
if you have more columns than you have rows, you can have at most m pivots.
So it can't have a
If you can't have unique solution, then always infinitely many solutions. Now, I've been known to trap people with a true-false question here. Is this statement true?
No,
Or
or
not
no
a solution system.
Provided it's consistent. Right. Always infinitely many solutions when consistent. But you could have an inconsistent system with lots of variables and it still wouldn't have any solutions. Any other comments yet? So now let's go back to what we were talking about a minute ago. If you started with an inhomogeneous system, AX equals B, and you reduce down to an echelon matrix, so let's just say, I'll call it U when it's echelon. U stands for upper triangular, which you'll see soon. So this is echelon form. And I have something here. How can you recognize when it's consistent? We've said this, but say it again.
When
It's just
there's no zero rows that have a 1 in the C. Or have a non-zero in the C.
So AX equals B is consistent if and only if for any row of zeros in U, there must be,
A non-zero value in C.
No,
consistent.
zero.
Zero, right.
So for any row of zeros in U, there is a corresponding zero entry in the vector on the right-hand side in the augmented part in C. In other words, you don't pick up an extra pivot in the augmented matrix from this column. Can you restate that in terms of the word rank?
Oh, the rank of the augmented matrix is the same as the rank of
So even when you augment, you don't pick up any extra pivot. That's equivalent to saying it's consistent. You guys buy that? So that's a restatement of what we said here. Can you give me a sufficient condition for AX equals B always to be consistent, no matter what B you put?
A is a pivot in
The
every column.
A is equal to n equals to m.
A is the identity matrix? No.
Well, but A is n by n still.
Is A equal n by n, but m, can n equal n?
A is B times the identity.
Yeah, because m equals n.
That big old elephant wants his turn here.
What?
Square.
Yeah, that's
When it's got a pivot in every
so
row.
m equals n, right?
Pivot in every row. Right, the mastodon gets to show up now. Right? When the rank equals m, which is the number of rows, there's no room for any zeros. Right? There's no zero rows in echelon form, so it's always consistent.
Consistent, not like unique.
So you sort of have this balancing act going on here. You have unique solutions when r equals n. You have consistency always when r equals m. And of course, you guys might want to talk about what happens when r equals m equals n.
That's a unique.
And it's the other
So in other words, we're starting with square matrices, right? M equals n, so you have square matrices. And if the rank is equal to the number of rows, every ax equals b is consistent and has a unique solution. So I don't has a unique solution. Since you were so happily understanding everything, I might as well give you another vocabulary word. Definition: a square matrix, and I'm going to underline square in red, because this word is used only for square matrices. A square matrix A is non-singular when this criterion holds. When r equals m. And it's square, so m and n are equal, and if the rank is equal to the size of the matrix, it's called non-singular.
Does that come from the idea of determinants and how like square matrices that are singular have zero as the determinant?
It's related to that, but it's a separate notion actually.
Okay.
So a square matrix, again square, is called singular. So please don't fall in the trap, as some of my former students have fallen, of using these words when you don't have square matrices. They apply only to square matrices. So a square matrix is called singular if
R is not. N is not equal to, if R is not.
R
equals-
doesn't,
If
R
any of
is
that
less
falls
than
Not equal to N.
so here's another one of these double negations. If it's not non-singular, in other words,
So like if that doesn't equal
R is not equal. It's in non-singular.
so r either doesn't equal m or doesn't equal n or doesn't equal.
well, it's square.
Right.
So if r is less than n, it's called singular. Now, there's always some confusion about which term is which, and I'll come back to this next semester, but let me just comment. For those of you who take some pride in your English skills, as opposed to your math engineering skills, in what context does the word singular show up in actual English? Not singular plural, in another context, as an adjective.
Unique.
Special.
Special, or standing out, right?
So it's special.
Something, a singular occurrence is something that is unusual or unexpected. So the math terminology is actually consistent with that. So the remark here is, among square matrices, in the world of square matrices, so round matrices aren't allowed in, among square matrices, the generic one is non-singular. What do I mean by generic? No, but what do I mean by generic?
Just your.
No.
If you just randomly assign things.
Right, you just picked one at random, most. So generic one, i.e., chances are, if you pick a matrix at random, it will be non-singular. The singular ones are special, they're rare. singular ones are relatively rare. So the words are consistent with the use in English of singular is more unusual, non-singular is what you expect. So you might puzzle yourselves for a while about why this is the generic behavior, why it's what happens most often and this is rare. We'll come back to that. So that's a definition. However, a very useful criterion for deciding if a matrix, a square matrix, is non-singular, or in fact more generally. So here's an important remark. Let's say useful in homework and exams. If you have an m by n matrix, so you could state it for square matrices, but I'm going to state it more generally. A, an m by n matrix, has rank n if and only if what? Let's see if we can put it together from what we've said. Where did we say rank n meant?
Every column has a pivot.
Every column has a pivot.
Right. It's
Unique solutions, provided it's consistent. So what's the one that's easiest because it's always consistent?
the AX.
The homogeneous system, right? If you take the homogeneous system of equations AX equals 0, it's always consistent. You already told me that up there. And what did we say though? If you have an m by n matrix whose rank is n, that means no free variables, which means, what about solutions of this? So the math language for this is that this system of equations has only the trivial solution. Now, math people are very fond of using the word trivial to put down their friends. You guys would never do that though, right?
No.
Oh, that's trivial.
Not my friend.
This is a technical term here. What do I mean when I say the trivial solution? So one way of testing out whether an m by n matrix has rank n is to say, can I find a solution of AX equals 0 other than the trivial solution, other than the 0 solution? That's equivalent. Having only the 0 solution is equivalent to saying no free variables, which is telling you rank n. I haven't said very much today, but it can feel like it's a jumble, so you have to take some time to actually absorb all this stuff, but it's not. If you just think about the picture of pivots and free variables, it all actually makes sense. Unlike some of the stuff we've done that makes your head hurt, this stuff shouldn't be that bad. All right, so I want to do an application here, and you will have web work like this stuff. So if you have a solution of AX equals B, what does that give you? What does that vector x that solves that equation tell you?
If you put the linear function t onto it, it turns into b. Like if A is the matrix for the linear function t, then t of x equals b.
Okay, so it's saying that you can get b as a value of the function, the linear function given by multiplying by a. If you think about our different interpretations, so we started off with this system of equations thinking about dot products of rows, and that's how we came up with these linear equations. What was our other understanding of matrix multiplication by vector?
Linear
Columns. What's the other interpretation of A times X equals B?
Linear combination.
Linear combination of columns. So if the columns are little a sub 1 up to little a sub n, you're writing the vector B as a linear combination with these coefficients given by the solution vector. So in other words, you have this following observation, which we're going to use a lot. The set of B's in our M for which AX equals B is consistent is exactly what set of B's?
Span of the columns.
It's the span of the column vectors. Remember what span means? All linear combinations thereof. Any vector that you can write as a linear combination of the columns, well, then that means you can write it this way, which means you can solve that equation. Conversely, if you can solve this equation, you have an X that satisfies this, which means B is a linear combination of the columns. So I'm now going to show you a concrete application of this. Any questions? So, example. For what vectors B is AX equals B consistent if I give you the following matrix A? First column is 1, 1, 1. Second column is 0, 1, negative 1. And third column is 3, 2, 4. And then there's a question mark. So how should I decide to do this? So yeah, from what I've said, we're talking about what's the span of these three column vectors, but how can I actually figure out what that is? Well, make yourself an augmented matrix. And put a B on the right with actual letters signifying unknown components for that vector. And now how are you going to decide if this guy's consistent or not?
Reduce
You don't need reduced.
But just
Just
put it in
get it in
echelon
echelon.
form.
Let's go for echelon. So here's a place where reduced is extra work that you don't need, right? The general advice would be if you're trying to write the general solution for a system of equations, go to reduced echelon form. But if you're not trying to get to that, you don't need reduced. So all right, let's do echelon form. What do I have? 1, 0, 3, E1. Read me the next row when I get rid of. So I'm going to use this pivot to clear out below him.
0,
0, 1, negative 1,
0, negative 4,
2 minus B1. Third row.
0, negative 1, 1.
Are you Gonna say something to yourselves yet?
You're gonna get a row of zeros.
It actually is gonna end up being sort of reduced, but that's sort of by accident. What happens when I use this one to clear out below it?
You get a 0.
Do I get another 0?
Yeah.
And then what do I have?
Makes 2. And that has to equal 0.
So we're back to what we've been talking about earlier. You have a row of zeros here. So to have consistency, this has to be, so consistent if and only if B, this vector B, whoever it was, satisfies the equation that B2 plus B3 minus 2B1 is 0. So now what can you conclude? Here you have these 3 vectors. The column, I'm not going to draw them to scale, obviously. The fact that there's a constraint equation for ax equals b to be consistent tells you what about the span of these 3 vectors? It's not all of R3.
Yeah.
Because in order for a vector to be in the span, it has to satisfy this equation. What do you think that makes the span be? Plane.
It's a plane that satisfies the.
And what do you think this vector, this equation is telling you about that plane?
So it's vector.
That's the equation.
Who's orthogonal?
-2, 1, 1.
So if I take the span of these 3 vectors, what I think you guys are telling me is that it is the plane whose normal vector is -2, 1, 1. So in other words, you're telling me that you think it's the perp of -2, 1, 1. Well, check it out. Is this vector in fact orthogonal to each of these? So you now have a way of using this consistency question to do stuff that we were doing in R3, say with cross products before. But this technique will work in more dimensions, and you will have web work to do that with later this week. Any questions?
Since spoiler alert, there's a homework problem like this, could you write it like the way we've been writing the general solution of X?
Could I write what? The general solution of the system of equations?
Yeah, B. Or could you write B as like a general vector? If you like solve for B1 and then write B in terms of B2 and B3 as like a linear combination.
Oh, right, okay, so that's giving the plane of B's in parametric form.
Yeah.
Yeah, you could do that, sure.
Okay, good.
But and that's totally different from writing the general solution of this equation.
Yeah.
Yeah. Okay. So let's see. So let's do another example here. For what B's is AX equals B consistent? So here's A now. Okay, so I'm making up the matrix as I go. Here's A. Let's see. You can probably figure out what I'm doing, but let's see. What am I doing here? Okay.
How are we supposed to?
If you don't have a clue, like,
It's very difficult.
All right, you'll probably figure it out soon enough. All right. It happened that this matrix is square. It didn't have to be. What am I going to do now? So I want to augment the matrix and then see what I end up with. So I didn't tell you the word. There's a famous word that goes with what we did here. This is called the constraint equation that B must satisfy in order for the system to be consistent. Right? It's constraining the vector B by that equation in order for the problem to be consistent. So similarly, I'm looking for constraint equations here, except I forgot to put the B. All right, so let's figure out what we get. So start reducing. Notice how polite I was with 1, 0, 0, 1 there. That was slightly premeditated.
did that to make it easier for yourself.
Okay, second row, I don't have to do anything with it. However, now we start having some stuff to do.
0, 1, negative 1.
0, 1, don't go too fast for me. 0, 1,
Negative 1.
negative 1,
5.
Oh.
and then what? B3 minus 3B1, right? Notice that what is happening here, and you're going to see this more tomorrow as well, is these are keeping track of your row operations. From the coefficients of what shows up here, you know what row operation you did. All right, what's the bottom row?
0,
0.
2, negative 2. Huh.
And what's on the right?
4 minus B. 4 minus B.
All right, we ain't done yet, folks. What happens now? Lots of zeros. You have junk, which actually really doesn't matter. And then what happens? You get a row of zeros. B3 minus 3B1 minus B2, because I subtract the second row from this row to get a row of zeros. And what about the fourth row? A bunch of zeros. B4 minus B1, and then what? Minus 2B2. So again, what do you now say? It's consistent if and only if what happens?
That's the only 0.
All those guys have to be 0, right? This has to be 0, and this has to be 0. Two constraint. We now have two constraint equations. So what does that mean? You expect then that, what do you think, the columns in this case are gonna span what, do you think? I'm not asking for equations, but what's your intuition? What's the rank of this matrix? Who said 3? Rank's 2, right? I've got 2 non-zero rows in my echelon form. How many, so therefore, how many free variables?
So on.
So if the equation is consistent, you expect to have 2 degrees of freedom in your solutions. And in order to have it be consistent, B has to satisfy 2 equations. So what do you think that's saying about the B's? You're in R4, one equation's giving you a hyperplane, another equation's giving you another hyperplane.
And they intersect.
You can see they're not parallel, they're not the same plane.
So they intersect.
At a line.
2 hyperplanes in R4
Our plane
is going to make a 2-dimensional plane once we actually talk about dimension, which is coming very soon. Okay. So I'm going to pick up with this example tomorrow, and we're going to look at it from a different perspective. So this finishes the first section of chapter 4.